morning, Townview. Welcome back to Chemistry Online.
Today we're going to be talking about Lewis structures. And to do Lewis structures, first thing you're going to want to do is figure out if what you're looking at is ionic or covalent. Now, how do we figure out if something is ionic or covalent? For something to be ionic, it needs to have a metal bonded with a nonmetal. In order for something to be covalent, it's got to be a nonmetal bonded to a nonmetal. So let's go ahead and take a look. Basically, if your first element is a metal, it's ionic. If the first thing is a nonmetal, then it's covalent. So over here we got H2O, no metals involved. This is going to be covalent. KCl, that's ionic. Lithium fluoride, ionic. Carbon dioxide, that's covalent. Magnesium, that's ionic. Nitrogen, that's covalent. H2 is covalent, and then aluminum, that's ionic. So this is the first step you need to do the Lewis dots. Now, what do Lewis dot structures show? They show you the outermost electrons only. So valence electrons are what you're looking at with Lewis structures. So the first ones we're going to do are going to be Lewis structures for ionic compounds, which are very simple. So I'm just going to start with examples. And you guys remember Lewis structures. So for potassium, that's going to be a K. And the total number of electrons that potassium has, valence electrons, is going to be 1. And then actually before we do this, what we want to do is figure out our formula. So potassium has a charge of +1. Oxygen has a charge of -2. So we're going to need 2 potassiums for every oxygen. Our formula is going to be K2O. All right, and then when we do our Lewis structures, we're going to have to draw both of those potassiums. So potassium, potassium, and then I'm just going to put my 1 valence electron out here. And then in the case of oxygen, oxygen has 6 valence electrons, so we draw the 6. So our first step for a Lewis structure for an ionic compound is we draw this. So I'm going to call this step 1, which just shows you the Lewis structures for everything involved. Step 2 is when we show the arrows. So the arrows just tells you where the electrons are going to go. In the case of an ionic compound, the electrons are going to be transferred. So potassium transfers its electrons to oxygen. So the arrows, this is going to be step 2. And then finally step 3, I'm going to draw that one on its own. So your potassiums both gave away an electron, and your oxygen now has all of the electrons. So all 8 electrons sit around the oxygen. Then we just put everything in brackets. So oxygen now has a charge of -2, and then potassiums each have a charge of +1. And these charges are nothing new, they just come from the periodic table. So oxygen's always -2, and then potassium's always +1. So that's step 1, drawing everything as it starts. Step 2 is showing the arrows, and then step 3 is showing the charges after the electrons have moved. The next one is going to be magnesium, nitrogen. So magnesium is going to have a charge of +2. Nitrogen has a charge of -3. So we crisscross, and then you're going to have 3 magnesiums and then 2 nitrogens. And then let's go ahead and write them out. So we got magnesium, 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 and then nitrogen, nitrogen. Our nitrogens are going to have 5 electrons each. So I'm going to start with those. And then our magnesiums have 2 each. This electron goes here. This electron goes here. This electron goes back here. This one goes down here. This one goes here. And then this one goes here. And then our final product, I don't have any room, so I'm just going to draw it over here. Our final product is the nitrogens are going to have all of the electrons, and then the magnesiums are going to have none of the electrons. The nitrogens are going to have a charge of -3, so total negative charge is -6, and then magnesiums are each going to have a charge of +2. And these charges are nothing new. You see these on the periodic table. Now, one other thing I want to show you guys is this is what I just showed you, and this is typically how DISD shows you these Lewis structures for ionic compounds. But don't be surprised if you see something that looks like this. So here we have our calcium. It's got a charge of +2. And then here we have a chlorine, and they put a 2 on the outside to tell you that you have a total of 2 chlorines. I've never seen Dallas do this, but just know it is something that they can do. All right, so let's go ahead and write down the steps for covalent compounds. So this is where Lewis structures actually starts. What we just did, I don't really consider that Lewis structures. This is Lewis structures right here. So we'll talk about the steps. So I want you to write down rules for drawing Lewis structures for covalent compounds, and then we're going to write out all the rules. So the first step is going to be to count the valence electrons in the compound. So find the element on the periodic table. You don't need to worry about any of this. The number of electrons equals its group number. You know how to figure out Lewis structures. So step one, you're going to count the valence electrons in a compound. So here's a compound, H2O. So hydrogen has one valence electron, but we have two of them. So that's 1 times 2, which is 2, plus oxygen, which has 6. So we have a total of 8 valence electrons. Over here, another example they give us is SF4. So sulfur has 6 valence electrons, and then fluorine has 7 times 4, which is 21, plus 6, sorry, not 21, 28, plus 6, which gives us the 34 total. So first step for Lewis structures for covalent compounds is always going to be to count up your valence electrons. Second step is we're going to put the least electronegative element in the center. It says never hydrogen, so hydrogens never go in the middle. And the reason for that is hydrogens, they only need 1 electron, which means they can only make 1 bond. The way I describe this to my students in class is hydrogen is your one-armed friend, and it can never have 2 bonds. So it doesn't have 2 arms. It can never look like this. Hydrogen's always going to be, it's going to look like that. It's only got 1 bond connected to it. So we can never put it in the middle because it can only bond to one thing. And you want to make single bonds from it to the other atoms. So, and then you also want to write single bond is equal to 2 electrons. Let me show y'all what that means. So H2O, we already counted our number of electrons. We said that that was 8. We're going to pick our least electronegative element, which is oxygen. And then we're going to put our hydrogens on the outside, and then we're going to make single bonds between the oxygen and the hydrogen. So that's all step 2. So next thing we want to do is we want to subtract these electrons that we just used up, because we only have a total of 8 electrons, and we want to know how many we have left. So we just used 4, because that's 2 right there, that's 2 right there. So we subtract 4, we have a total of 4 electrons left. All right, so here it says add the remaining electrons in pairs to the outer atoms first to satisfy the octet rule. So let's go back to H2O. So H2O, which has a total of 8 valence electrons. We have our oxygen in the center. It's single bonded to 2 hydrogens, so we subtract 4, and we have a total of 4 electrons left. So it says add the remaining electrons in pairs to the outer atoms first. Our outer atoms are going to be hydrogens, and hydrogens, they can't accept any more electrons. So let's discuss our exceptions to the octet rule. So the most important one is something you should already know. So hydrogen can only hold 2 electrons. So right now, hydrogen is already holding 2 electrons. You can't put any bonds on it, and you also can't put any electrons on it. So as soon as you see an answer choice that looks like this, that's going to be wrong, because hydrogen cannot hold any more electrons. Beryllium is not an example you guys need to know, so you can go ahead and cross that one out. This one is one I do want you to know because of a shape that boron makes. We'll talk about that in the next video where we talk about shapes. But boron is stable with only 6 valence electrons. And in college, you're going to come across examples that include this exception. So the central atom could possibly hold more than 8 valence electrons, which basically throws the whole octet rule out the window. Basically, any element that comes after phosphorus could potentially hold more than 8 valence electrons. It could hold 10, it could hold 11, it could hold 12, but this is not an exception you need to worry about today. The 2 exceptions you need to know is hydrogen can only hold 2 electrons, and boron is stable with only 6. Let's keep going. So next step says put any remaining pairs or single electrons around the central atom, and then we call these lone pairs. So let's get back to our example. So we have oxygen single bonded to 2 hydrogens, and we have a total of 4 electrons left. We can't put them on hydrogen, so we put them in pairs on the oxygen. So one thing I see students do very often is they'll put one here, one here, one here, one here. That's not okay. So over here it tells us that we want to put them in pairs, which means our electrons need to always be paired up. So 2 over here, and then 2 over here. All right, and then last step, I want to rewrite the last step. So first thing we're going to do is check octets, which means you basically want to look at every element involved and you want to see its octet. You want to make sure it's happy. So is hydrogen happy? Yes. Is hydrogen happy? Yes. Next we look at the oxygen. Is oxygen happy? So each one of these bonds is worth 2 electrons, and then each pair is worth 2 electrons. So oxygen has a total of 8, both of the hydrogens have 2, and everybody has an octet, so everybody's happy. If not everybody is happy, what we're going to do is you're going to use, so write this, use double or triple bonds until everyone is happy. We'll discuss that when we go over examples. All right, so let's go ahead and move on to some practice. Okay, so here's our first one. I'm gonna go through these in order. So step 1 says we're gonna count up the total number of valence electrons. So nitrogen has 5. Hydrogen times 1 has 1 times 3, because we have 3 hydrogens. So that's gonna be 3 plus 5, which gives us 8 total valence electrons. Next step, we need to pick our central atom. That's gonna be nitrogen. And then we're going to make single bonds to it, to all the other hydrogens. So we have 3 hydrogens, and we just use 6 of our electrons because each one of these bonds is worth 2. That leaves us with 2 valence electrons. Next step is to put those electrons on the outermost electrons first. So we can't put any of them on hydrogen. Our next step tells us to put them on the central atom. So there they go. So now we have 0 electrons left. And then our last step is to check octets. So hydrogen is happy, hydrogen is happy, hydrogen is happy. And then our nitrogen has 2, 4, 6, 8 valence electrons, so nitrogen is also happy. And that's it. So that's the Lewis structure for NH3. Let's go ahead and move to the next one. So here our carbon has a total of 4 valence electrons. Our hydrogen is going to be 4 times 1, so 4. Total of 8 valence electrons. Next thing we do is we pick our central atom. That's going to be carbon. And then we put our hydrogens all around it. So we're going to use the north, south, east, west positions. And then we create single bonds between the carbon and the hydrogen. That's going to be a total of 8 electrons. So we subtract 8. We have 0 electrons left. Then we check our octets. So hydrogens are all happy. And then our carbon is also happy. All right, so the next one, silicone has a total of 4 valence electrons. Chlorine has 7 times 4, which is 28, plus 4, which puts us at 32 valence electrons. Our central atom is going to be silicone. That's the least electronegative. And by least electronegative, we just mean it's the farthest away from fluorine. And because covalent is always nonmetals, the farthest from fluorine would be silicone or carbon. So we have 4 chlorines. One's going to be in each spot. So chlorine, 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 and chlorine. And then we put in our single bonds. And then we subtract. We do 32 minus 8. That leaves us with a total of 24 electrons. And then we can go ahead and start placing them. So that's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. So we just used up all of our electrons. And now if we check our octets, all the chlorines have 8, and then the silicone also has 8. All right, so next up we have CO2. So carbon has a total of 4 electrons. Oxygen has 6 times 2. That's 12 plus 4, so a total of 16 electrons. Our central atom is going to be carbon, and we're going to put our 2 oxygens on the outside, and then single bonds from the oxygen to the carbon. So 16 minus 4, because that's how many electrons we use so far, that leaves us with 12. Then we place our electrons on the outermost electrons first. So 2, 4, 6, 8, 10, 12. And now if we look at our octets, we see that oxygens are both happy, but our carbon is not. So carbon only has 4 electrons in this case. So what's it going to do? Carbon is going to pull electrons away from this oxygen. So these 2 electrons here are going to be pulled towards the center. And now carbon and oxygen get to share those. So oxygen still has 8, and now carbon has 2 more than it used to. And then it comes over to this side, does the same thing. It pulls these electrons over here. And now carbon gets to pretend like it's got 8, and both of the oxygens still have 8. So that's going to be it right there. So anytime you put in all your electrons and you find that something doesn't have an octet, that's when you start using double and triple bonds.
If you don't know how to do chemistry, hit that subscribe button. Let's go!